Welcome back for another flight computer video. Today we're looking at the takeoff performance computer, or the TOPCOMP, which was copyright in 1971 by Richard Fritz. This is a two-sided device. The back side of the device just has the instructions for use. You can tell that the construction is a laminated cardboard, whereas the front of the device has a piece of plexiglass and these cardboard slides here for the different variables that we'll use in calculating our required takeoff distance. Also, it's not evident, but there's a card here, and the card has two sides. So one side is for fixed pitch propellers and the other side is for constant speed propellers. And in order to see how this device was used, we will take a look at an example problem, and we will compare the results of the TOPCOMP performance computer to the way that pilots would normally derive this information, which is looking at the pilot operating handbook. Today we'll be looking at a Cessna 150, and in particular the takeoff distance table that is present in that handbook. So let's just find the answer the way we would traditionally, and then we'll use the TOPCOMP. So we'll put in these parameters. So 41 degrees Fahrenheit is in this column right here, 5,000 foot pressure altitude, a concrete runway, so we have a hard surface runway listed right here, 0% runway slope. Now there's no factor for runway slope within this table, a 10 knot headwind, which would be listed right here, and maximum gross weight, which would be 1,600 pounds for the Cessna 150. So we essentially just go to the proper cell in the table and we can read our answer right here of a ground run would be 780 feet. Now we'll do that same calculation on the TOPCOMP. So we just pop in all of those variables. We start with our temperature. Our temperature is in this window up here. So we set that as close as we can. So we'll set it to 40 degrees Fahrenheit. And the next thing we need to do is set our pressure altitude. And we do that by manipulating the cardboard slides here until it lines up on our pressure altitude. So this arrow right here lines up on our pressure altitude of 5,000 feet. Now, it's a little unusual in that in order to set the arrow that you want, you have to move a cardboard tab for another variable. So this cardboard tab is labeled runway surface, but what I'm actually doing by moving it is setting my pressure altitude since the arrow is pointing above. Okay, so moving along. We also have a concrete runway. So we'll take our next tab and set it here to concrete runway. And then we have a 0% runway slope, which we can set, which is quite nice. So I set that right there above the wind. I set my wind as a 10 knot headwind. Now, headwind is listed, there's two scales here. So we have a red scale for percentage of our takeoff speed, or we have a black scale, which is for wind, headwind, or tailwind in miles per hour. And our question is in knots, so we'll have to convert that. So 10 knots of a headwind will be 11.5 miles per hour. So we'll use the black scale here, and we'll set it right about there. Again, notice I'm using the black numbers, not the red numbers, to set that at 10 knots or 11.5 miles per hour. And then finally, we're at maximum gross weight. So our gross weight will be 100% here. All right. Like that. And the final step is to look at our aircraft model, which is a Cessna 150, and follow that arrow down, and we pick up our required takeoff distance in feet of roughly 980 feet. And so the difference there is about 25%. 25% longer takeoff distance when calculated with the TOPCOMP. And if we want to know why, we can take a look at the supplementary instructions that came with the device. And it says, TOPCOMP was designed to provide realistic estimates of takeoff distance, not the optimum performance obtainable with a new aircraft flown by a professional test pilot. And this was done deliberately for your safety. And it's true, when when we learn how to interpret these tables, we're often taught that we should add a safety factor on top of these figures. And the TOPCOMP is doing some of that for us. So it's quite nice. You could take this device and you could set it up so that you could calibrate it for your own piloting ability and your own aircraft. And you would do that by just going out and making note of how long your takeoff distance was, then setting the parameters to whatever was present in the environment at the time, and then making a little line somewhere on this last slide for your piloting ability and your particular airplane. So in that regard, the TOPCOMP is quite nice. It's also got the ability to tweak some things that we couldn't tweak within the table, so things like runway slope or being able to scale our maximum gross weight. So it's a handy device. There's also one other calculation that we can get from the TOPCOMP, which is our percentage of rate of climb for various pressure altitudes. So if we take this same problem and we go back into our POH and we look at our maximum rate of climb data, for 5,000 feet and 41 degrees Fahrenheit, our rate of climb will be 470 feet, as opposed to 670 feet, which is what it would have been at sea level. So that's a reduction of about minus 70%. And if we look at TOPCOMP, well, we have to interpolate between these categories to be able to get to it, but between 4,000 and 6,000, our rate of climb will suffer from either 74% of our sea level value to 59%. And so right in the middle there, we have something like 66.5%. And again, you can tell that the TOPCOMP is being more conservative than the POH, which is fine because, as we know, these values were conducted with a new airplane and a professional test pilot. So that's how the TOPCOMP works. A nice, simple device. And if you are learning to fly, it's great to be able to sit down and manipulate some of these different variables to find out which variables have the most impact and how do they add together or subtract together in different ways. So for example, if you were interested in trying to find out, given a situation where you could take off downhill with a slight tailwind, would that be better off than taking uphill with a slight headwind? You could use this device to set those parameters and figure out the answer. So that's all for our video today, and thanks for watching.